Okay, now let's get started. Just as a reminder, project number 5 is due next week on Friday at noon. That's November 30th. That will be the last grade that we will have before the final exam. Regarding test number 2, here's the listserv post that I put out there a few days ago. Overall, the grades are very, very, very similar to the grades that we had last time. Mean score was 81%, and last time we had a mean score of 82.95%. Median for this test was 83.5. Last time it was 85. So very similar scores. There are a few comments I want to make about commonly missed problems on the exam. The first one is 1A, just very short here. You need to find a second order sample regression model. The common mistake the students were making is that they forgot to put the interaction term into the model. So the interaction term needs to be in there in addition to the quadratic terms. Another problem, number 1B, we're still having some problems with respect to when should I use a confidence interval, when should I use a prediction interval. The key thing that was bolded in the problem was 1. And when you're talking about prediction interval, you're talking about one random variable, and you're trying to come up with an interval for it. If I would have said something instead, such as find the approximate 95% interval estimate for the mean lifetime, then that would have been a confidence interval. So that's the difference. And lastly, number 2B. For this problem, I didn't unfortunately word it as well as I would have liked. The problem asks, well, when is this F star going to be large? And what I was hoping that you would do, and I did take off points if you didn't, because I didn't word the question as well as I would have liked. What I was hoping that you would do is actually look at the formula itself. That's why the formula was given there. And for a large F star, what that's going to mean is that the second SSE that you see in the equation, this one right here, is going to be a lot lower than the first one that you see in the equation. Because if F star is low, then that means, if F star is high, what that's going to mean is that this model is, with these additional variables, is really contributing to lowering the sum of squared errors. So if the first SSE, which is called 1 and 2 here, if the first SSE is high relative to the second one, and all this stuff's in the numerator of F star, that means F star is going to be large. And so that's what I was originally intending for an answer there. But I did take off points if you didn't relate it necessarily to the equation. Okay, so that's all I had to say specifically about the exam. Do you have any questions? Okay.
I have a question.
Yeah.
Yes, it's like how the way to compute the AIC.
Yes.
You say how to fit the largest model, right? At the beginning.
Excuse me?
You have to fit the largest model. To compute, using your code to compute the AIC.
Which problem are you on?
1F.
Well, to compute the actual AIC itself, you don't need to fit the largest model. The only reason why that's needed for this fit.stat function is when you are actually calculating the CP. Or wait a second. Yeah, the CP. So for the AIC, you don't need to fit the largest one. So just be careful about how you use my code. You need to make sure that you fully understand what's going on with it.
So we don't have to use your code here?
You wouldn't have had to use fit.stat, no.
but we should have the same result.
Well, what you could have done is just, yeah, you will have the same result. And the AIC, you could get that, for example, there's a function called AIC. I just used this fit.stat function because I also needed, I believe I needed some R squares as well. So if you notice, for example, in 3 here, notice what I did? I did it the simplest way.
All right, my second question is that how do we determine the largest function, the largest equation? Is depend on...
You mean the largest model that contains all the predictor variables of interest in a linear form.
In the linear form, only in the linear form.
In the linear form. At least that's how we were using this corresponding statistic that's needed for it. That's how we were using it in Chapter 9 when we were in the model building process, Step 2, and we were trying to decide which predictor variables to consider further in the model building process. Other questions? Okay, let's move on then. Okay, page 1040 of the notes. We're going to talk about something called a variance inflation factor. And this is another thing that helps you diagnose when multicollinearity happens. And I think for 3 separate chapters we've talked about multicollinearity. I really wish the authors of our book would just simply put the entire discussion all together. Unfortunately, they don't. And for some reason, I've decided to continue doing it in the order that they have put everything in. So remember what multicollinearity is. It exists when you have predictor variables that are basically explaining the exact same information about your response Y. So then the question comes about, if I have 2 predictor variables that are explaining exactly the same thing about Y, WHY, would I need both predictor variables in the model? And in fact, if you do have both predictor variables in the model, this can cause problems. Problems in terms of your standard errors are extremely large. Remember how we use these standard errors again for the B's. Remember how we use those standard errors. They factor into t-tests where we use that to judge the significance of a particular variable in a model. Also, what can happen is if you have, let's say, and I demonstrated this in Chapter 7 when we were actually simulating data, when you could have, if you went out and took another sample, you could have now the signs in front of the B's, a plus or a negative sign, change because of this multicollinearity problem, and thus changing totally your interpretation of the effect that a particular variable has on the response. Also, you can have computational problems. In case I didn't say this already, you can have computational problems. Because what ends up happening, without going into all the details, is that this X prime X matrix that we have to invert to find B, that can be very, very difficult to invert if I have very strong multicollinearity problems. In fact, well, I'll just say it becomes very difficult to invert. If you take a course like 970, you probably talk about that in a little bit more detail than what I'm talking about here. So we want to be able to detect when multicollinearity happens. And we talked about, for example, you could simply look at a scatter plot between, or a scatter plot matrix between all your variables, which allows you at 2 at a time, 2 predictor variables at a time, determine, do I have a strong relationship between them? Well, the next method that we're going to use to detect multicollinearity is actually better. It's called the variance inflation factor, VIF. And this is what it looks like. Just symbolically, we'll denote the variance inflation factor by VIF parentheses K. This is the book's notation, so if you don't like it, blame them. Notice the K here. It goes from 1 to P minus 1. This corresponds to, we're going to have a variance inflation factor for every single predictor variable in the model. Okay. And this is how we calculate it. take 1 minus the coefficient of determination, or what we often just simply call r squared. But this coefficient of determination notice has a subscript k on it. I'll explain why in a second. Take 1 minus an r squared, and we invert it. Okay. This r squared is not the normal r squared that we've been seeing so far. Rather, it's an r squared from a model where xk now is the response variable, and all your other predictive variables are predictive variables in this new model. So what this is measuring is the association between all these other predictive variables with the one variable of interest, let's call it x of k. So if that r squared is large, what does that say about the relationship between all the variables and this one predictor variable? What does it say if I have a large r squared in this situation? Yeah, we need to be careful about what we say correlation, because when we say correlation, we typically mean between two variables. Here, what this is actually measuring is, you can say like a multivariate, you can say dependence, in terms of how all the other p minus 2 predictive variables, how they are related to our one predictive variable of interest called x of k. If it's large, then that basically says that all the other predictive variables are explaining basically the same kind of information as x of k. So relating this to what we had seen previously in Chapter 7, where we were basically looking for multicollinearity amongst just two predictive variables at the same time, this allows you to look at possible multicollinearity problems that involve all the predictive variables, or subsets of your predictive variables. So it's not just necessarily just two. Because you can think of a situation where, let's say that you have x1, x2, and x3. And if I calculate r squared 1, and suppose it's 0.99, what that's saying is that together x2 and x3 are basically very, very closely related to just x1 itself. In other words, a linear combination, I should say, of x2 and x3 gives you the same information as x1 would. And thus, you will have multicollinearity problems. Now, look what's going to happen then to this VIF if I have an r squared of 0.99. So the VIF subscript 1 is going to be 1 over 1 minus 0.99, or in other words, 1 over 0.01 or 100. So, if we have multicollinearity problems, are you going to have a large VIF or a small VIF? You're going to have a large one. So that's what we look for.
And it doesn't, this measure doesn't take options of interaction.
It could. I mean, you could definitely calculate this with interactions, quadratic terms, or other stuff in the model. I just simply did this one particular example. Okay. So let's instead say that r squared 1 was 0.1. What's my VIF going to be? So let's say r squared 1 was 0.1. What's VIF? I'll do the math for you since no one wants to speak up. It's going to be low. And that makes sense. What this is saying, if you have a low r squared, 0.1, that says, well, x2 and x3 are not really that closely related to x1. Thus, I'm not going to have a multicollinearity problem. So then the question comes, well, how high does VIF have to be for you to be worried that you might have a problem? And this is just kind of a general rule of thumb that our book gives, is that if VIF is greater than 10. Now note, corresponding to our discussion or quick question that we just had, that when you have interactions in quadratic terms in your model, you're likely, or you could, I should say, have large VIFs. This is not necessarily something to be worried about unless you're having computational problems. But why would you have large VIFs in those situations? Well, if you look at the relationship between x1 and x1 squared, well, depending upon what the x's are, you could have these be very closely, have a high correlation. I can say correlation because I'm just talking about just one predictor variable in its transformation. Okay, so let's take a look at the MBA guard data set once again. There's a function R called VIF. It's in the CAR package that does these calculations for us. So let's say that we've actually estimated our model with our 4 predictor variables that we found from Chapter 9. And we put the results in mod.fit. We use VIF. And notice all the VIFs are relatively small, less than 10. So we have nothing to worry about. Great. Just as an illustration then of how this calculation is actually done, what one could do, let's say for MPG itself, estimate a model such that MPG is the response. The other 3 predictor variables are the predictor variables in this model. I put the results in mod.fit.mpg. I summarize the fit. I pull out the R squared from the summary, and I take 1 over 1 minus the R squared, and I get exactly the same as we had above. Now back in Chapter 7, as I mentioned, we looked at multicollinearity. In fact, we had one particular example where I artificially constructed some data such that we would have multicollinearity. Just as a reminder, we had a response variable y. We had 2 predictor variables, simply x1 and x2. Notice the high correlation between x1 and x2. And we definitely saw that in our scatter plot. And so what would be then the variance inflation factor for this example? Well, I now estimate my model, do VIF, and as you can see, the VIFs are extremely large, which is what we would expect in this situation. Okay. That concludes section 10.5. Are there any questions? Okay, section 10.6. Now we get to one overall example that we can look at that applies the stuff in Chapter 10, so that now we will be able to actually conclude one overall model, and we're going to look at the MBA guard data set here. Make sure you take a look at the example that's in the book for a second example. So at the end of this section now you will have enough experience where if I give you a data set, you're going to be able to find one overall model for it. Now, in Chapter 11, we're going to look at some refinements of stuff that if we have problems that can happen, how can we handle them? Various problems that we haven't necessarily discussed in this class yet. But for a large number of data sets now, after this section, you'll be able to go through the process of model building. So from start to finish. So the MBA guard data set. Again, in Chapter 9, we found these 4 variables are variables that are of interest to us that we want to consider further for inclusion into an overall model. At the beginning of Chapter 10, then, we looked at these added variable regression plots for these 4 predictor variables. And if you remember, these plots help you get an idea of what form should the predictor variables be in your model. Should you have a quadratic term, for example? And what we found was that maybe with MPG, maybe a quadratic form, a quadratic term might be helpful. With height and field goal percentage, it looked like we were specifying the variables correctly by just a linear term. With age, it was even questionable if a linear relationship existed. Maybe age wasn't important at all. In fact, I think we had a p-value about 0.08 in Chapter 9 when we were testing whether or not age was important or not, given the other variables were in the model. So it was kind of even questionable if we should even consider age. But we thought, well, let's just consider it further. We can always take it out later if needed. But also, if you remember, too, and from past discussions, I kind of hypothesized that maybe an age squared might be helpful. And this is an example where, if you have a particular knowledge about the data, about the subject that the data comes from, this is where you can apply it. In that, while it's questionable if we should have even age at all, I want to leave age in there for now, and even consider an age squared based upon my knowledge of the subject. And we can see what happens. Okay. So what I'm going to do now is examine two quadratic terms, MPG squared and age squared, and also all pairwise interaction terms. Again, this is a place where if your knowledge of a particular subject is sufficient, maybe you can narrow down which interactions to look at. But I didn't feel comfortable doing that, so I decided to look at all pairwise interactions, and plus there wasn't really that many to look at. So then to sift through all these extra terms I'm looking to add to my model, what I decided to do was forward selection using simple t-tests. So if you remember from Chapter 9, I wrote a function called test.var that helps you do these tests. And where the forward selection process starts is with the model that just has what you call the main effects terms in the model, MPG, height, field goal percentage, and age. And what I'm going to do is test the interactions one at a time. So I'm going to specify my HO model, specify my HA model, which is exactly the same except for I add MPG and height for one of these interactions. I put the results from test.var into an object called mpg.height, and this is going to contain a p-value. I'm going to do that also for all the other interactions. And notice here are the squared terms. Just as a reminder for these squared terms, notice how, again, I use the I function to actually put a squared term in my model. And so we get all these p-values. I put them in a data.frame, and this is what we get. So what we're looking for with a forward selection process is we're looking for small p-values. And what we see, the smallest p-value is MPG squared. Not surprising given our results from the added variable plots. So I'm now going to add MPG squared to my model. So now my HO model, when I'm doing this forward selection process, is going to be exactly the same before, but with MPG squared in it. And then again, I'm going to look at all my other possible HA models that have one additional term in it. So again, with MPG and height, notice here's my MPG height interaction. Notice also I have age squared in there. And I look at all my results. We see that MPG and age have a significant interaction. So it's kind of good now that we were still considering age further, even though it had a p-value of about 0.08 when we were looking at just the model that had the main effects terms in it. Otherwise, if we want to consider age further, we would have missed this. So let's add MPG and age to my model. So notice the additional terms that I have in there for my HO model. I do a similar thing as before. So MPG height. Here's the additional interaction. Page 1046. Now MPG in field goal percentage. I have a marginally significant interaction. It's kind of borderline. 0.038. It depends upon whatever I would use my alphas. It is kind of a low p-value. But let's say that I add it to my model. And we continue. So here are the three additional terms now I have added to my model. And I get to a point where I look at all my p-values and notice all of them are large, so I stop. Now, what about cubic terms? What about three-way interactions, four-way interactions? You can look at those as well. But obviously, the higher the order, you could say, the interactions are, or the higher the order the transformations are, it becomes more and more difficult to interpret. So typically, unless I have prior knowledge about a particular data set where I suspect a three-way interaction, I typically would not look at it. Others may disagree, but that's how I usually will approach the problem. So, we'll be able, if you wanted to, you could look at that. I'm not going to here. The key thing is to remember this: is that you're trying to find a mathematical equation for reality. Do you think that you're going to find the exact mathematical equation that exactly that perfectly models what you're trying to do? No. What you're trying to do is come up with a good approximation for reality. And so that's always my philosophy with modeling. Okay, so let's examine these models a little bit further. Remember that this MPG field goal percentage is kind of iffy if I wanted to include it or not. And so what I decided to do was estimate the model without this interaction and also estimate the model with the interaction here. Just get a general sense of what's going on. Take a look at the summary. So you can see, for example, with this MPG field goal percentage, here's my corresponding p-value. Some things to look at then. Look at the adjusted R squared. Look at the R squared. Well, I didn't do this here. One could look at the AIC. One could look at some of these other measures that we've talked about as well. So here's the adjusted R squared and R squared for the bigger model. So what do you think? Should we include this interaction in the model? Excuse me?
It's responsible for a couple percent in variation.
Yeah. Well, yeah, it doesn't hurt. This is what I said in my comment. If you don't have access to it, it might be kind of small, so I'll just read it. This comment was made August 15, 2006. Does not improve the adjusted R squared much and is marginally significant. I would not include it now, but look to include it later if any of my diagnostic measures suggest problems with the model, like outliers that may be fixed through its inclusion. That's a possible approach. When I was going over my lecture before class today, and I didn't look at the comment first, I had concluded, yeah, it doesn't hurt. Why don't we just leave it in the model? It does improve R squared a little bit. It is marginally significant. So, as you can see, back in 2006, I was quite a different person from what I am now, I guess. So maybe with 6 years of experience, 6 more years of experience, my thoughts have changed. But the reason why I bring this up is that what one person says is the best model could be different from what another person says is the best model. But notice that both of the choices here are justifiable, and that's the key. Especially, many of you are going to be writing papers eventually for journals. You need to be able to justify whatever you choose for like a model. As long as you can justify, even though some people might be able to justify a different model, as long as there is clear-cut justification for what you say, you're fine. Okay. Notice I could not justify adding, let's see now. How about height and age? There's no way that I could justify including that in the model. It will be hard to get a paper published with having height and age in the model. Okay, so the key is be able to justify and just realize that somebody else might be able to justify a different model too. There can be more than one okay model for a particular data set. Okay. Let's see here. So also by looking at this output, the way I did above, it's kind of like sort of a backward elimination step too, because I want to make sure that I always have significant terms in my model. And by doing that forward selection there, I'm leaving myself open that once I add a term to my model, something else now may be not significant. If you look back in the p-values, everything's okay. All of them are small. We already talked about this B. And C, and we talked about this a little bit in Chapter 8, and that is when I look at these p-values, we'll look at these up here. For MPG age and MPG age interaction. In this particular case, to make a judgment of, well, now does maybe a term need to be removed from my model, I only look at the corresponding interaction. So I always look at, let's say, the highest order term containing that particular variable. Because what can happen is that one of these p-values could now be large. That doesn't mean that the variable is not important. It's just due to the mathematical structure of the model now, that could happen. And the thing is, you need to always focus on the highest order term containing that particular variable. So also, like for example, when I'm looking at MPG squared here, if I'm just looking at MPG itself, I would not look at this p-value. I would only look at this p-value. Okay, well, what about the AIC? You could also use an AIC to do what we did here. So let's take a look at how one would approach this. So I estimate a model that has where I'm going to start. So with the 4 predictor variables in it, and I put that in the step function for object. I'm going to do both forward and backward. So it's, basically it's a stepwise forward selection process. And then for scope, I say where to start and where to end. And notice where I end here is a model that has all those interactions plus those 2 quadratic terms that we were concerned about. So I begin with the model that has just MPG, height, and field goal percentage, and age in it. Here's my AIC. And I look, well, should I add any variables? Well, the variable that lowers AIC the most, or the term that lowers AIC the most, is MPG squared. No surprise. So that gets added to my model. Can I lower my AIC anymore? Well, MPG and age lowers it the most, so I add that to my model now. Can I lower my AIC even more? Well, look at this. MPG field goal percentage, that was marginally significant before, it does lower AIC. So I suggest let's add that to my model. And then finally, I can't lower my AIC anymore. So it finds basically the same kind of model that we found. That doesn't always happen, but that's what happened here. Okay. Are there any questions? Okay, now let's examine some diagnostic measures, meaning that we want to look for outliers, we want to check for constant error variance, we want to check to see if I have any influential observations, and so on. So to help you out, again, what I've done is I have this function, examine.mod.multiple. What did I actually call it? Hold on. Yeah, examine.mod.multiple.final. It's in the examine.mod.multiple.final.r file. To use this function, you need to actually run the file. Of course, you could use the source function to run it. So you get the function into R, and it's set up in very much the same way as my other 2 functions. And first of all, make sure you only use this function now. Don't use the other ones because this one is the best of them all. Just we needed to have some other ones to build up to a certain spot. There are some minor differences. In particular, this is how you run the function. So mod.fit.obj is equal. Put in your model, mod.fit1, or the results from fitting your model. And we're going to look at the model that does not have this MPG field goal percentage interaction in it. First.order, what this corresponds to is the first order terms in the model. How many do you have? We have 4. Now the way that I've set this function up, and it's not perfect, is I always put all the main effects, the first order terms first when I use the LM function. Okay, so you need to do that. So you need to have MPG, height, field goal percentage, age. List those first in the LM function. I do want to do some tests for constant error variance, And let's also do the box Cox transformation as well. See what happens. Okay, so we get a lot of plots. Lots and lots of plots. Page 1052, then, we have the original plots that we've seen already in the past. So I'm not going to spend time on them. It's just some box and dot plots of our response variable and our predictor variables, just to make sure that they are reasonable. We don't have any, let's say, data entry errors. 1054, we have the residuals versus estimated mean response. What's this plot used for? Constant error variance. What do you think? Looks pretty much like a random scattering. So that's good. That's good. Then we have a plot of R sub I, which, just as a reminder, this is the studentized residual versus the estimated mean response. We have the light red lines, which correspond to the 0.00, oops, I'm sorry. Let's see, this is T.995 with degrees of freedom of n minus p. So it's a 0.995 quantile from a t distribution. This is going to be the 0.005 quantile from a t distribution. And the darker red lines are the Bonferroni adjusted t values for your t distribution, where alpha is 0.05. So it would be something like, let's see, T1 minus alpha divided by 2 times, I believe that's n minus p degrees of freedom. Just double check that, but I think that's what it is.
So the inner lambda for alpha equals 0.01.
A 0.01. 0.01.
Adjusted one is 0.01.
Yeah, that's just what I chose. And notice, this is great. Nothing's outside these borderlines. So good. So T sub I versus estimated mean response. T sub I is a studentized deleted residual. And these borderlines are exactly the same, except for the degrees of freedom is now n minus p minus 1. Okay? And this is good. Everything's within inside these borderlines. Okay. Now I should also mention that with these plots too, when you run my function, I'm not going to run it here because it takes a while to go through all these plots. When you run this function, you have the opportunity to click on points and identify the points in a very similar manner to what we've done in other versions of this kind of a function. Okay. Now, let's make this a little bit bigger. There we go. Now we have residuals versus our predictor variable. Remember how I said first dot order equal 4? This is where this comes into play. You have to look at the function yourself to understand how this comes about. This will do a plot of the residuals versus the first 4 predictor variables. And what we're doing here is, again, making a judgment of have we specified these predictor variables correctly. This goes back to chapter 3 when we first looked at a plot like this. It's not exactly what an added variable plot gives you, but it gives you a similar idea. And notice we have scattering of points throughout. Random looks like random scattering of points, so it looks like the predictor variables are specified correctly in our model. Our histogram of the residuals, well, that's kind of mound shape. Kind of has a normal distribution, kind of. Our QQ plot looks pretty good, except for we have maybe a little bit of a deviation here. But overall, it doesn't look to be too bad. Okay. Now the new plots that we haven't seen previously, when we run this kind of a function, is all these plots that we were looking at before that examine influence. Okay. The first one is DF fits versus observation number. Can someone tell me what DF fits does again? How does it measure influence? Anxious to have some turkey, and just decided to just kind of say, I'm not going to worry about this until after Thanksgiving. Remember what DF fits does. It looks at how does y hat change when let's say the ith observation is removed from your data set. So I should say, how does y hat sub I change when the ith observation is removed from the data set? And we have two sets of borderlines here. The first one, the lighter red corresponds to where we would expect for large data sets these values to fall within. If instead we have a small to medium sized data set, then we have these darker red borderlines. What would I characterize this data set as? Well, it's not small. It's probably maybe medium in size, maybe large. But what we see here is we do have some observations, and again, I can click on these points on my plot to identify them. We do have some observations that are outside this inner band, or these the inner borderlines, and we even have some that are maybe just barely outside the bigger borderlines. So what this indicates to us, then, we want to take a closer look at these observations. This is not necessarily something that says, okay, our model's junk. What this is saying is, okay, we need to follow up on these points, see if we can figure out why this is occurring, and if this is something we need to be worried about. How about Cook's D? Does anyone remember what Cook's D does? Exactly. So it basically does the same thing but as DF fits. But now it looks at all of your y hats. How does the ith observation affect all of your y hats? And remember, we said this is a more serious problem to have if we have a Cook's D that is large. And if you remember, to judge large, we look at a quantile from the F distribution. It's the 0.5 quantile. I don't remember if the degrees of freedom is n minus p or not off the top of my head. But anything larger than that quantile says, okay, we have a problem. Fortunately, we don't have a problem. And lastly, we have these DF betas. Because there are actually 6 terms of our model, the 4 main effects, we have an interaction, and we also have a quadratic term, I'm going to have 6 sets of these DF fits to look at. Remember what the DF fits examine. I should have started off saying that. It examines how does your B change, your estimated beta, how does it change given if the ith observation is in the data set or if it's not in the data set.
So it doesn't become beta 0?
Typically you don't need to. So the inner lines here, the lighter red ones, again, is the border lines for a large data set. The outer ones are for small to medium size. See if we can get all this on one page. And what we see here is that we do have some that are outside these lighter red lines. So we have some stuff we want to follow up with. Fortunately, nothing's outside the darker red lines, though. So that's good. So I'm sure now all of you are probably thinking, okay, we must have a small to medium-sized data set. We don't have large because Everything's inside the darker red lines. And then lastly, we can look at the Cox Transformation Plot. Notice how 1 here is just a little bit outside this 95% interval. Suggesting maybe there might be a problem with non-constant variance. Although, obviously, it did not appear in that plot that we looked at when we were looking at the residuals versus estimated mean response. Okay, so some comments. These comments are much what I've already said, but I do go into some other details. We've already talked about this. The residual versus estimated mean response. We don't have evidence of non-constant error variance, although it's kind of borderline when we look at the Cox plot. How about we actually look at the corresponding tests? So what are these tests telling us? Do we have reason to believe that we have non-constant error variance? No. These p-values are kind of large. They're not. I should say they're not small. So, even though we have this Cox thing coming up as well, maybe it is. I'm left with believing that we don't necessarily really have a problem. And I guess I like looking at the plots. I like looking at what the plots tell me more so than necessarily what the Cox would tell me, if they disagreed, in which they do here, to some respect. We don't have any problems with outliers. Now we have to address the influential observations. So what I did was when I looked at those plots, just, I wrote down what the observation numbers were. I put them as the row numbers for the MBA GARD data set so that I could look at these individuals more closely. Okay. So I have some comments about these individual in 1062 if you want to flip back and forth. So we see, for example, Bagley here. He's observation number 7. Notice he only played in 10 games, and his height's 210 centimeters. That equates to, for those of you who are not familiar with the metric system, 6'10". That's a tall guard, very tall guard. And in fact, I won't do this, but if you go back to the corresponding DF beta plot for height, well, this is where you're going to see Bagley stand out. So, this is kind of to be expected because he is quite different from the rest, but it doesn't necessarily mean he's hurting the model. Let's see. Bogues. I think his first name was Tyrone Bogues, if I remember right. I'm sorry. We can also look at the DF betas as well. Bogues is on the other extreme for height. Where's his height? 160 centimeters, which is 5'3". Couldn't you imagine Bogues playing Bagley? It's like, Bogues would be down here guarding Bagley. I don't think that would be a good matchup. But anyway, he also stands out on the DF beta plot too for height. Let's see. Cheeks. I think this is Maurice Cheeks at the end of his career. I think he's a coach now in the NBA. He was 35 years old, so he was kind of old. Well, 37 years old. Sorry, he was 37, which is kind of old, but it's sure not as old as I once thought it was. But anyway, his DF beta for age stands out too. Green, number 37. Notice how he only played 13 games. I guess also Cheeks only played 35 games. In particular, look at Cheeks, Green. Look at his ppm, 0.7704. Now remember how we saw that Michael Jordan, which is observation 52, right below green there, had the highest by far ppm of 0.8291. So this green is scoring a lot of, when he gets in, he scores a lot of points. But notice he only got in 13 games. Look at his minutes per game. 6. Number 48, Jennings. He is way down here. He only played 8 games. But overall, what we see here, maybe I'm getting ahead of myself too, we see some similarities amongst these individuals, and that's what you're looking for. So you're trying to figure out, why is this occurring? See if maybe there's something in common. And what we see here is that a lot of these NBA guards are playing low minutes per game in a low number of games. For those of you who are not familiar with the NBA, well, for those of you who are familiar with the NBA, how many games are there per season, as long as there's not a strike? 82. Okay, so you can see when you have 10 games, 35 games, 39 games, 13 games, these players are not getting in a lot. And when they do get in, they don't play that many minutes per game. So, what are these players? Well, these are probably players that are sitting, let's say, at the end of the bench. But the only time that they get in is when the game is out of hand. Often you refer to this as garbage minutes, meaning that whatever they do in the game is not going to really matter because it's pretty much the outcome has been decided. One team's going to win. They typically get in at the end of the fourth quarter. And the competition that they're playing against is against the players on the other team that are sitting at the end of the bench who don't get in except for at the very end of the game when the game's out of hand. So these are not, you could say, the regular players that you normally would see. So that's a common characteristic. Then that might make you think, okay, well, maybe how can we take advantage of that, knowing that common characteristic? Well, I'm getting ahead of myself, so just stay tuned for that. Okay, so histogram, QQ plot, they're mostly okay. And so what I decided to do was only observation 21 and 37 were outside the small to medium-sized data set range. And they were kind of close to the borderlines. But they're the only ones that were outside. So I thought, well, let's take a look at what happens if I remove just one at a time, number 21, and see what happens with my model. I do the same thing with 37. So notice here I have this in caps. Just because I am removing these observations does not mean there's justification for removal. I'm only doing this to examine influence on the bees. So just because you have an observation that's influential does not mean you automatically remove it. Please realize that. We're only doing this right now to see what the true effect is from these observations. So without observation 21, I put the results into something called mod.fit1.wo21. How do I remove observation 21? Well, when I specify my data argument, I say MBA bracket, and if you put a negative in front of the observation number, that tells R, remove it. Okay, very simple. So I get my estimated model, get the B's out, and what I decided to do was, let's look at the percentage change in these B's from when observation 21 was in the data set versus when it wasn't. So how do you calculate percentage change? I take the new B's, subtract off the old B's, divided by the old B's, round it by to 2 decimal places. What I focus on is the actual coefficients to variables on the model. And we do have some change. So without observation 21 in my data set, my MPG age interaction drops by 17%. That gives me a little bit of worry. But one thing that's very good is this, is that the signs on these Bs remain exactly the same as what they were with or without observation 21. So it's not going to change the direction of the association that we are saying exists by this model. So that's good. Also, it's not changing significance either. So when I remove observation 21, I still get these significant terms. So that at least makes me feel a little bit better. You can look at observation 37. You see something similar. For example, with MPG squared, the change is 11%. But again, the B's have the same signs, and they're still significant. Okay. Well, while I don't like to see a change as I wouldn't say that we have a large change here in the B's, but we do have some change. And while I don't normally like to see that, the nice thing is, again, the B's have the same signs, and they're still corresponding to same significance. So because of that, I would be okay to use this model. It would be okay to use this model. But as I've mentioned before, there's justification for other models. So, corresponding to what I was saying, that a lot of these influential observations seem to correspond to players that are not regular players. What that could mean for us is that we're basically missing something here. We're having a hard time characterizing the PPM for these guards who don't play a lot. They're not regular players. And in fact, I don't really see a good way to characterize these players in our model.
Why not add something like number of games?
Yeah, what you could do is maybe find another variable that takes that into account. But it's not just games, it's minutes per game too. And I think there's maybe some other factors as well. And so, because I'm not necessarily comfortable, at least, to try to characterize who is a regular player versus a player that's not a regular player, what could be done is fully justifiable, is remove all NBA guards who are not these regular players. Again, how do you quantify them? There's not a set way. So what I decided to do was actually remove, let's see now, guards that play in less than half the games. Okay? Remove the guards that play in less than half the games. That ends up being 16 guards out of 105. Notice what...
You don't examine why some of them might be just injured.
The problem is getting that information too. At least originally when I was first doing this, working with this data set, it wasn't as easy to do as you could now, but still it would take some time to figure it out. But what this means, though, by removing this, it has an effect about how I can use my model, and something that you need to remember whenever you do something like this. And that is, you are changing your population of inference. Before, my population was all NBA guards. Now, it is just NBA guards who play in at least half the games. And so let's say, if we were actually, let's say, using this model and wanting to publish the results in a paper, you need to state that, because this is now a smaller population of inference. But in the end, maybe it's not a big deal, because who really cares about these guards who are not regular players? Normally, you're more interested in these regular guards. Maybe some of you disagree with me, but I'm more concerned about how Michael Jordan plays rather than one of these Other guards just doesn't play that often. Now, what happens then when you remove this? Well, you have to look through. You have to go back now in this model building process. You could even go back all the way to step 2, because now variables that were significant before may not be significant now. What I ended up getting was this particular model. Notice, for example, we have MPG and free throw percentage now in there. Didn't have that before. Don't have age. So you can see it's a different model. But whenever you change your data set, this can happen. I don't give all the details here because I don't think we need to spend another 20, 30 minutes going through the entire process. And I have a fairly decent model. I do have Michael Jordan as an outlier, but that's not necessarily something that worries me because I know that Michael Jordan is the best basketball player ever. Sorry, non-James fans. And I do have some diagnostic measures that showed some observations may be influential as well. But overall, I wouldn't say necessarily that the model was worse than the model that I had originally concluded. So I think this particular model is justifiable, just as my previous model is. Well, what if when I had my data set that had the MPG field goal percentage interaction term, in the data set that had all the observations, what happens if I added this interaction term? Well, again, you could go through all the diagnostic measures once again, and here's just some of them that I brought out. And you can see that there are some similarities. There are a few observations that are now a little bit past the borderlines now. So we have a little bit more influential maybe observations, maybe. And again, what you do is you need to actually remove, maybe one at a time, these observations from the data set and actually look at the B's. You can actually look at the Y-hats too, although I didn't earlier. You can look at the Y-hats too to see if they change. So I refit the model. So previously, this was my B for MPG and field goal percentage with a p-value of 0.038. Without observation 21 and 24, which I found to be potentially influential, now my B, let's see, where is it? There it is. Now this is my B. Notice how the sign has changed. Thus, my interpretation changes. And in fact, you can see that my B has changed by 63%. That's big. That's big. So the direction of association is, I'm sorry, while the direction of association stays the same. Wait a second here. Am I missing something? Because the direction of association is changing.
No. The beta is still positive.
Excuse me?
The beta is still positive.
Well, I mean, I have a, okay, I'm sorry, I'm looking at the wrong one. I'm sorry.
Sorry.
Negative. They were both negative before, I'm sorry. I was getting confused, sorry. So the B's are, I'm sorry, the B's were still negative. The B's were still negative. Let's see now. The t-test is still significant, but the B's have changed by 63%. That's I'm sorry. That's where I was worried. So that makes me a little bit more worried about how good the model is comparatively to our two previous models. So overall, if I had to pick one model, I pick the model that has for all the observations without then this extra interaction in it. But as I said, other models are justifiable too. Okay, that concludes Chapter 10. Any questions? Well, in terms of, I think you're saying look at the y hats. Yeah, I mean, you can do that too. For some reason, I didn't do in the notes, but actually, before class, I was examining that with this original model, and without the first observation that we removed, y hat changed by 11%. So it was still kind of the same amount.
When you examine that, are you examining for this particular for data for this particular player, or
For the particular player, let me just go back.
basically you take the axis of the specific player, right?
Hold on. So when I remove observation 21, the y hat changed by 11%.
But why can't for what?
For observation 21.
For the set.
Yeah, so those corresponding observations, like I'm sorry, that observation 21, I removed it from the data set, refit the model, got the y hat, compared to my previous y hat with observation 21 in the data set, and it changed by 11%.
But that's expected because we see that these are out west. So if
Well,
we read it without them, it's expected that the change will be like.
It's not surprising, but it's not necessarily always going to happen. You know, these measures that we look at allow you to identify potential problems, and so it's not unexpected. But the thing is, it doesn't tell you how bad of a problem necessarily it is in the context of your data. That's why I looked at the actual percentage and saw 11%, which again was kind of borderline about would I be worried or not. And you know, there might be cases where you just can't solve a problem either. And if that's the case, you know, what you're going to have to do if you're, let's say, trying to publish a paper, you're going to have to state, here's my model, but I had this particular problem. I had this particular problem. I tried these potential solutions. It didn't work out, and so I'm left with this is my best model. You know, there might be other types of regression models, and that might be helpful. We'll talk about that in Chapter 11 as well, which there are some models that allow you to get Bs that are not as influenced by influential observations. Are there any other questions? Okay. Well, we just ended class early today. So that's it for today.